I'm going to perform an example where we calculate the modified bearing life for pump bearings. And the purpose of this example is to demonstrate the incorporation of some of the real-world conditions into our estimations of bearing life. Calculate the modified bearing life for these pump bearings. Let me diagram simply the shaft and the bearings on the shaft. These are matched bearings. That means there's two together, and they are back to back, meaning these are the load angles. So they are matched back to back bearings. Now the maximum radial load is 1.45 kilonewtons, and the maximum axial load is 11.5 kilonewtons. The operating temperature is 85 degrees Celsius. And the rotation speed is 3000 RPM. The lubrication is by oil bath with an oil viscosity grade ISO VG68. The inside diameter of the bearings is 60 millimeters, and the outside diameter of the bearings is 130 millimeters. The data that we have about the bearings says that the dynamic load rating is 104 kilonewtons. The static load rating is 76.5 kilonewtons. We don't need that right now. And the fatigue load rating, which is the load P sub U, meaning the load for an unlimited life, is 3.2 kilonewtons. We're going to break this down into 9 or 10 steps to calculate the modified life given these real-world conditions and some assumptions for reliability. There's something else we need to know, and that's something about contamination. We're going to suffice it to say right now, given there is typical contamination, which consists of minor ingress of contaminants or grit. So the main keyword here is typical contamination. The first step toward a solution is to calculate the equivalent dynamic bearing load. To do so, you need some catalog data. There's typically a threshold E above which the thrust load must be accounted for. And for this problem, the E value for the back-to-back bearings is 1.14. So how do we use that? So we're going to use one equation. If FA, axial over radial, so the thrust is above a certain amount, above that threshold, then we have to use one equation. If it's below that amount, we have to use a different equation to account for equivalent dynamic bearing load. That's F sub E. Our F sub A, where was it? Here, 11.5 kilonewtons. Our F sub R, 1.45 kilonewtons, which gives us a value of 7.9, which is greater than the E value of 1.14. Therefore, we're going to use the equation that the equivalent load equals x2 times the radial load plus y2 times the axial load. And so those values have to be given as well. So x2 here is 0.57 and y2 equals 0.93. Now, if the value was less than 1.14, we would have used y1, which is 0.55. But it's not. It's greater than 1.14. So therefore the FE equals 0.57 times the 1.45 plus 11.5 times the FA, which is, let's go backwards, 0.93 times the FA, which is 11.5. And that equals, oddly enough, it comes out to 11.5 kilonewtons. That's just a coincidence that it's the same as the original axial load. So now we've found the equivalent dynamic bearing load, which is good. We're going to have to use that later. Step 2 is to calculate basic dynamic rating life. Here we still haven't accounted for contamination at all. We haven't accounted for reliability. So that's going to be the L10. These equations are set up for 90% reliability. That's why it's called L10. And then if we're going to calculate it in hours, the reference life is 10 to the 6th. And we divide that by the RPM. And we need 60 minutes per hour so that we can convert RPMs from minutes to hours. And then we have the C value over the FE value. And since this is a ball bearing, it's cubed. If this was a roller bearing, it would be to the 10⁻³ power. Now this C value, because these are two bearings, we have a higher load. Okay, we don't deal with them individually because they work together. They're back to back. So if we're going to deal with them individually, we would reduce this max load by half, and we'd say, okay, they get half of it each, but we can't do that because the two bearings back to back behave differently than one bearing would behave by itself. So we have to deal with them differently. And for matched bearings, C sub matched equals 1.62 times the C for the single. And so here's the dynamic load rating for a single bearing. So 1.62 times C single equals 1.62 times 104 kilonewtons, which is 168.5 kilonewtons. So if we plug that value into this equation, we plug this FE value into this equation, we get L10 in hours equals 10 to the 6th. What was our RPM? 3,000 times 60. Got to watch those units. So we're going to get lifetime in hours. The units have to cancel inside here. 168.5 kilonewtons over 11.5. So this is not that unusual, but our equivalent load is quite a bit less than our rated load. That's to the third power for a ball bearing, and that gives us 17,476 hours. Step 3 is to find the actual viscosity. We're going to have to use that given the operating temperature of 85 degrees Celsius. That's going to give us the horizontal axis, that's T-op, and then oil viscosity grade is going to give us the curve. So then we have to take that data, take that information, and we have to be given a plot. Here's a plot of on the horizontal axis. Again here, we have the operating temperature, 85 degrees Celsius. We go up to the oil viscosity grade, 68, so this curve for 68. We take that line over to the y-axis to find the viscosity, and then we have to estimate the viscosity there. And I estimate that's about 13 millimeters squared per second. There's the units. Units are millimeters squared per second for viscosity. So we're going to mark down here 13, viscosity equals 13 millimeters squared per second. Now we've seen step 1, calculate the equivalent dynamic bearing load, FE, which led us into step 2 to be able to calculate the basic dynamic rating life without taking into account anything about the environment. Now we're on step 3, step 4, and on, where we are accounting for the environment. So step 4 here is going to be another plot that we have to look at to find the needed or rated viscosity for the system. What goes into finding the rated viscosity is the mean diameter. So we got the inside diameter plus the outside diameter over 2 gives us the average or the mean diameter. That's 95 millimeters, and that's going to be what we look at for the horizontal axis. And then we need the speed, and that's going to be the curve that we look at. And given those two pieces of information, we're going to read off the rated or the needed viscosity for this machine. So here we have the plot where we look at the mean diameter for the horizontal axis. We had a mean diameter of 95, so just shy of 100 here. And then we look at the curve. We have 3,000, and then we read off the rated viscosity, V1, somewhere around 7 millimeters squared per second. So we notice up here in this corner you have low speed and diameter, so you need a high oil viscosity because the pressures are typically high and maybe anti-wear additives. Down here in this corner you have high speed and diameter, so a lower viscosity oil may be sufficient, but you should be concerned about, with that high heat, lots of friction resulting in overheating of the bearings. So we're going to take this value of 7 and go back to our calculation. So here the rated viscosity is 7 millimeters squared per second. Now this next step is simple. Calculate the lubrication factor, which is the viscosity ratio, K or kappa, where kappa is the actual, or K is the actual over the needed. So that's eta over eta1, and we got 13 over 7, so that equals 1.8. So we saw that steps 3 through 5 here were about lubrication. Now we're going to talk about contamination and its effects on fatigue life. So step 6 is to account for the effects of contamination on fatigue life. And this step is to find the eta value. And the key word for the eta value was that we were looking at minor grit ingress. So here's the table that you need to find the eta value. Value for bearings with a mean diameter of less than 100 millimeters. Ours was 95 millimeter mean diameter. If you have typical contamination, minor grit ingress, you get an eta sub C value of 0.2. So eta equals 0.2. We also need our fatigue load limit, which our PU was 3.2 kilonewtons. And we need our equivalent load. Again, that was 11.5 kilonewtons. We need to put all those together into one value. It's eta PU over FE. Plugging those numbers in, 0.2. Now, we have matched bearings. Once again, we have two bearings. And with matched bearings on fatigue life, you get a doubling of the fatigue life. So for our matched bearing, we're going to get a doubling of the fatigue life. We're going to get 6.4 kilonewtons of fatigue life. Let me transfer that data over here. PU matched equals 6.4 kilonewtons. So that's 6.4 over 11.5. That comes out to 0.11. Step 7 is the last one we need a chart for. We need the eta PU over FE value that we just calculated for the horizontal axis, and we need the K value for the vertical axis. So that was 0.11 is what we're going to be looking for, and the K value we got was 1.8. Here's my chart. This is the contamination times the ratio of the unlimited fatigue life over the equivalent dynamic bearing load. And so if we keep going over to the right, the equivalent load is less than the fatigue limit times the contamination factor. So you can get lots of fatigue life. And if you go to the left, contamination is really bad, so you get a lower fatigue life. Our curves here are the lubrication factors. So if you had what I would call a poor lubrication ratio, so the lubricant is less viscous than necessary, you're going to get a shorter life. But up here, if the lubrication is more viscous than necessary, you get a longer life. Now you may not get all the efficiency you want, but you're going to get a longer life out of your bearings. So we had 0.11. We go up to the curve for 1.8. It's close to 2. And that takes us over to about 4.5. So I transfer my value over here to 4.5. So steps 3 through 5, we're accounting for the lubrication. Step 6 was contamination. Step 7, put it all together, lubrication and contamination. And now I need to use those values, use that value, or put it all together in step 8 to calculate my modified or adjusted life. So my L10 modified in hours is going to be that modification factor times the L10 that I previously calculated in hours. That's 4.5 times 17,476. So that's 78,642 hours. So because I have such a high amount of lubrication, I have more actual lubrication viscosity than is needed. That gives me a longer life than expected. And additionally, because I have such a low load, my load is only a little bit less than twice what the unlimited load would be. So I get a longer life, essentially. But that is for 90% reliability. 90% reliability is the reliability value that's baked into these equations. So what if I want 95% reliability? I have to go to a chart for reliability factors, A sub R, for the different values of reliability. 90%, 95%, 99%. If it was something off of this chart, I would have to interpolate. But I picked something on this chart, 95%. So that's a reliability factor A sub R of 0.64. And I simply have to multiply that by the L10 hours to get that reliability in the equation. So let's do that. So my value for 95% reliability, I'm going to take the AR times the L10M HR. That value is 0.64 times the 78,642 hours, and that gives me about 50,000 hours. And there's another step I could do, which would be compare with the expected life of this type of equipment. And this is the type of machine that might be used in continuous 24-hour use. It's a pump, and the specification life for this type of machine is 40,000 to 50,000 operating hours, and that jives with the value I got, 50,000 hours. So that would give us a step 10 compared with the expected or the specification life. So reviewing very briefly, first I calculated the equivalent dynamic bearing load, then the basic dynamic rating life, the L10 in hours, then found the actual viscosity and the needed viscosity, step 4. Step 5, calculated the K, actual over needed, for that lubrication factor. Step 6, found the contamination factor, eta, multiplied that by the ratio of the unlimited fatigue life over the equivalent load. Step 7, looked at a plot. The horizontal axis was that eta PU over FE, the curve, I should say curve. The curve was the lubrication factor. From that, I got my application modification factor, A sub m of 4.5. So I used that 4.5 to calculate the modified life, 4.5 times 17,476. That gave me 78,642. Then I plugged in 95% reliability, which simply made me multiply the previous calculated value by 0.64, which gave me 50,000 hours. And then step 10, compared that with expected specification life for this pump of 40,000 to 50,000 hours.